Folks, today we're going to be talking about speed and velocity. Now, when we have an object moving, we pretty much naturally want to know how fast it's moving, right? If I'm pitching a baseball, so last time we talked about distance and displacement, if I pitch a baseball, you don't really care that I threw it from the pitcher's mound to the home plate. Like, that's kind of the minimum that a pitched baseball should be able to do. We want to know how fast it goes there, right? Like, that's the big thing that we focus on. So, when we talk about speed, speed is the rate that distance changes over time. That's the definition of it. It's how far it's gone in what period of time. So, if I throw a baseball real slow, that distance is going to be the same, but the time's going to take longer. And no one cares about that if it's too long, right? Like, if I just roll that ball on and in there, no one cares. When we talk about speed, the symbol that we'll use for speed is lowercase s, and the units are always going to be meters per second. So when we talk about these things in physics, we're always using those metric units, and we're going to be using meters per second. So just to kind of give you an idea, you probably walk around 2 meters per second. Your car goes about 25 meters per second. If you're biking, 25 meters per second would be like driving on the highway. So there we go. So when we talk about speed, we actually define it in two different ways. And then we'll talk about velocity, and these two ways kind of break down the same way for velocity too. But the first way is average speed. So when we talk about average speed, that's the total distance traveled in a period of time. So we take the total distance and we divide it by the whole time that object was traveling, or the time that we were measuring, or whatever it is. But the important thing here, if we're doing the average, it's averaged over this period of time. It's not an average like we'd normally take an average, like take 4 measurements and divide by 4 to get the average of those 4 measurements. This is averaging the speed over a period of time. Now the thing about that is it doesn't account for any variations in speed. So if I said I drove my car 10 miles in 5 minutes, you would go, actually that's really fast. I'd be going 2 miles a minute. I should never drive that fast. If I drove 5 miles in 10 minutes, you go, you're driving half a mile each minute. You'd come up with about 30 miles per hour. But I could have driven at 50 miles per hour and then stopped for red lights a couple times. And that would bring my speed down, right? So it doesn't give me the whole picture of what the speed is the entire time. When we calculate average speed, the formula for it is distance over time. So we'll just use our symbols for distance, which is capital D, and time, which is lowercase t. Now, we can throw that into a triangle and do S is equal to D over T. If the triangle works for you, great. If the triangle doesn't make any sense to you, don't struggle to figure out the triangle. I feel like using algebra is really the best way. And we're going to use some basic algebra to do these problems. So, speaking of problems, let's work a problem. So in 2009, Usain Bolt ran the 100-meter dash in 9.58 seconds. What was his average speed? Well, when we're doing these, we want to identify what we know. So anytime, now that we're in physics, anytime that we do a physics problem, it's always best to write down what you know. So we've got the distance there is 100 meters. 9.58 is the time. And we're looking for what the speed is. So, and this is something I tell every physics class, physical science, honors physics, AP physics. If you're doing one of these problems, it's always best to write down what you know, and that's going to make it easier to solve. Now we can take a look at this and we can say, hey, I've got everything I need. Now all I need to do is write down my formula. So my formula is S is equal to D over T. And I'm solving for S. So I can just plug in what I already have. So I have 100 is my distance over 9.58. Now all I have to do is do the math, right? Oh, and I get 10.43 meters per second. So that is his average speed. Now here's the thing. He started at rest, right? Because when you start 100 meter, you're at rest. His top speed is actually going to be significantly higher than this. Probably something like, 11, 12, maybe even 13 meters per second. As he runs, he's going to be speeding up, right? So we'll talk about speeding up and acceleration next time we get together. So that's one type of problem that you'll see, just straight up calculating what the speed is. The other thing that we could see as a problem is trying to determine how much time it takes for a motion to occur. So if we have this problem, a 95 mile per hour fastball moves at 42.5 meters per second. So this is imperial units, right? Our English units that we don't use for physical science. Here's our metric units. These are the same. If you type in the conversion into Google, 95 miles per hour, you'll get 42.5 meters per second. So the ball travels 18.5 meters from the mound to the plate. How much time does the batter have to react? So once again, let's go through and identify what we're given. We're given meters per second. Anytime I see meters per second, that tells me that I've been given a speed. So I can write down what my speed is. 18.5 meters. Meters always tells me distance. So I write down D for distance. And then, how much time does it take? Now sometimes I get lazy and I write, how long does it take? Well, how long is just asking for how much time, right? So we're looking for, oh, that's the worst question mark ever. It's like a 2 with a dot under it. Oh well. So, S is equal to D over T. Now, if you want to use the triangle, go back and look at the triangle. But if I want to solve this for time, algebraically, here's what I would do. Since time's in the denominator here, I would multiply it, maybe have a quick giggle right there, and then I got to get rid of this S over here, so I'm going to divide both sides by S. So if I take the distance divided by the speed, that'll tell me how much time it takes. Now that makes sense, right? If I went 100 miles and I'm going 100 or 50 miles per hour, I would get 100 divided by 2 hours. So that makes a lot of sense to me. If we're just doing it in metric, it's going to work the same way. It's just not going to be as intuitive as if we were talking about driving a car 100 miles at 50 miles per hour. It's going to take 2 hours. So when we do that one, so 18.5 divided by 42.5. Now here's the thing. We should expect something less than a second, right? Like baseball would be a whole lot easier if the ball traveled slower. We get 0.435 seconds. So 0.435 seconds is the time it takes from when it leaves the pitcher's hand to when it reaches the plate. So less than half a second, which makes a lot of sense, if you've watched baseball. Let's do one last type of problem. So if you drive a car for 25 meters at 25 meters per second, so once again, that's about 62 miles per hour, and you drive it for 40 seconds, how far do you travel? So we're given the speed is 25 meters per second. we're given the time is equal to 40 seconds. And we're looking for how far is really asking for the distance, right? What's the distance you travel? So now I know S is equal to distance over time. And I want to get the distance by itself, right? So I'm going to multiply both sides by t, and that gets me d is equal to s times t. So I move the t over here, and then I just flip the sides to put the thing that I'm solving for on the left. So the speed would be 25, the time is 40. Oh, I know 25. I'm not even going to get out my calculator because I know 25 times 4 is 100. So that's going to be 100 plus an extra 0, 1,000 meters. Be a whole kilometer. Okay? So that's how we would calculate speed, or average speed. The other thing that we want to talk about is instantaneous speed. So the instantaneous speed is the speed at one instant in time. Now, the difference between average speed and instantaneous speed is instantaneous is right at that precise second. So if I'm looking at the speedometer of my car, it tells me how fast I'm going that second. It's instantaneous speed, not the average speed. It wouldn't make any sense to make a device in my car that would tell me my average speed because I'd be driving around at 35 miles per hour or whatever. And then when I stop, instead of going to 0, which would be my instantaneous speed, my speedometer dial would just kind of go and approach 0, which doesn't tell me how fast I'm going. If I had a speedometer that worked like that, I'd never know how fast I was going precisely. I'd just kind of have the average. Anyways, so back when I was a kid in the 80s, the place that I lived, it was common back then to basically have cops measure 2 lines on the road and then basically wait for cars to go by. So this was before radar guns were widely available. So if my car is going down the road and it passes by these 2 lines, sometimes there would be a cop there timing how long it took you to go through the lines. Well, are they measuring instantaneous speed or average speed? So, hopefully you took the time and thought about it yourself. They'd be measuring the average speed, the average between these 2 points. So the instantaneous speed would be 1 instant, so less than a second, less than a microsecond, 1 instant in time. This is telling me what the average is in between these. And if I was going and speeding and I saw 2 lines painted on the road, not that I was driving around in the 80s, but you could just kind of pump your brakes in the middle here and then speed off, or slow down before you saw these, stop, speed off again, and they couldn't really go, oh, you were speeding. Anyways, the other thing that we want to talk about, and I'm not going to focus on this too much, is velocity. A lot of times we'll use speed and velocity interchangeably, but basically velocity is the rate that displacement changes over time. So the symbol for velocity is a v, and the units are meters per second. Since we're talking about displacement, that means displacement, unlike distance, has a direction, right? So my velocity should always tell me which way I'm going. Sometimes we'll write that as positive and negative, or sometimes we'll say east, west, right, left, up, down. Those would all tell me that direction, and that would make it a velocity instead of a speed. We can do the same thing to calculate average velocity. It's just going to be displacement over time. And once again, we would have the same instantaneous velocity, the velocity at 1 instant in time. So velocity calculates the same way as speed, The only big difference is that velocity has a direction with it. So it gives me a little bit more knowledge about what's going on. So your speedometer in your car doesn't measure velocity, because if you throw that car in reverse and then, watch your speedometer still goes up because it's measuring how fast you're going speed-wise. It doesn't give you a negative velocity because you're going backwards. Not that it should. Okay, so that's all I have for speed and velocity right now.